In SAC 113, problem number 1, we're asked to draw a bunch of free body diagrams. In the first case, we've got a crate with an eye hook in opposite top corners. Let's go ahead and draw the crate. I'm going to draw a sketch first, and then we'll go for the free body diagram. So we'll go ahead and put the eye hooks in there, one right there, one right there. Consider them to be part of the crate. And then we've got a rope extends upward from one of the eye hooks, goes over what must be a rather large pulley, and comes straight down, because these two segments are supposed to be vertical. So we'll put the pulley in there. And this crate is suspended at rest from that device. So we're supposed to draw a free body diagram. I'm going to look at it directly from the side. Now we're looking at one corner, but at the same elevation as the middle. There's the corner sticking out at us. And let's see, we've got a rope touching it right there, extends away from it in that direction. I'll call that T for the tension in the rope. Now, this is one single rope segment. As it passes over the pulley, all the pulley does is change the direction of it. It doesn't affect the tension. So where it's attached to the crate over here, the eye hook in this corner of the crate, it's applying the exact same tension. And it is important to use the same symbol there to emphasize the fact that the tension, these two forces are equal. They're both unknown, but they're equal to each other. And then we got the gravitational force exerted on the crate by the Earth. We'll call that W for weight. And that's all there is. We get everything that's touching it. The rope is touching it there. There's a rope segment touching it there. And then the one force exerted on the crate by an object that is not touching the crate, namely by the Earth, and that force is the weight force. So we got the whole thing. I want to emphasize that this is the free body diagram over here. This is our answer to 1A. Okay, let's look down at the next one. We got a boy pushing a crate across a flat horizontal concrete floor. So I'm going to draw a sketch of that situation as well. Get a crate right there. He's pushing downward and forward on it. So let's have his hands pushing on it right there. There's his arm, and have him leaning forward a little bit, pushing down and forward on that crate, and it's going in that direction. There's a sketch. Now we got to get a free body diagram for the crate. Okay, I draw the crate itself. Then I'm supposed to indicate all the forces acting on the crate by means of arrows. Well, there's a floor touching the crate, exerting a normal force in the upward direction and a frictional force in the direction opposite that of the motion. So the object is going rightward in this picture. The frictional force must be leftward. We've also got the Earth exerting a force on it. That'll be the weight, and then the boy exerting this force on it at an angle. I'll draw a horizontal in here. There's a dotted line, and that force is at an angle, I'll call it theta, where theta is equal to 25 degrees below the horizontal. Now let's see if I got everything that's touching it covered. The boy is touching it. Got that covered. Let's call this, I should label it though, F. It's a boy. I have to label it for it to be a correct free body diagram. Also, it's a constant velocity, so the acceleration is 0. Might as well write that down. Up here, I could have written the same thing. A is equal to 0. This one, the velocity is obviously constant because the object is at rest. So we got a constant 0 value of velocity. Here we got some constant non-zero value of velocity, but in either case the acceleration is 0. So we don't need an acceleration arrow on the diagram. So the boy is touching it, got that covered. The floor is touching it, normal force and frictional force, got that covered. And then the earth exerts a force on the crate without touching the crate, namely the weight force, and we got that covered. So let's move on to part C. A woman in the loft of a barn hoisting a crate upward by means of a ridgepole. If we look at the roof of a barn, and I am going to draw a sketch here to start with. This beam, this horizontal beam that runs along the ridge of the roof, is referred to as the ridgepole. And there's a rope extends downward from the ridgepole to a pulley attached to a crate. And there's a woman in the loft of the barn. Let's get her inside there. She's pulling upward on this segment of the rope here. So this is evidently a see-through roof here. So there's one of her arms, other arm there, and have her pulling upward on that segment of the rope. And in this case, the crate is going upward. I'm reading it. The rope passes under the pulley, goes straight up. She's pulling upward. The instant in question, the rate at which the woman is raising the crate is increasing. So there's some acceleration in the upward direction. Okay, we've got enough in our sketch to go ahead and draw a free body diagram. We'll put the crate in there. I do want to remember that there is some acceleration. Acceleration drawn as an arrow that's not touching the crate, unlike all the other arrows. The arrow should be either the tail touches the object and the arrow extends away from it, or the head is touching the object. Arrow is extending toward it like we do sometimes with a normal force. And also we're supposed to consider the pulley. Crate plus pulley is what we're drawing the free body diagram. So this is actually our object that we're drawing a free body diagram of. We've got the rope is touching it right here. Where it extends away from it, it's going to exert a tension force. I'll call that T on the pulley. Over here, we've got another segment of the rope extending away from it. The tension in this rope is the same throughout, where it passes over a pulley. All the ideal pulley does is change the direction of the rope, the direction in which the rope extends. It doesn't change the tension in it. And the force exerted by a rope on an object is always directed from the point where the rope makes contact with the object away from the object in the direction in which the rope extends. So we've got two upward forces here, and they're both of the same value. It's important to use the same symbol to make sure that we're not telling the reader that we don't know that both of those forces are identical. Then we've got the Earth exerting a downward force called the weight force. And that's it. The only thing that's touching that object is the rope. That extends away from it at 2 points. And then the only thing that can exert a force on our object without touching it is the Earth, that gravitational force that we've talked about. So this is our answer. I don't know if I boxed the last one in, but it's important to note that this is our answer. The thing to the left is just a sketch. This is the free body diagram. Let's move on down to part D. This is the last part. Person is pulling a crate. Again, I'm going to draw a sketch of this situation. I have a flat asphalt driveway by means of a rope. Here's the rope. And then put a person in there. And they're pulling on that rope. There's the arm of the person. Pulling on that rope, and the rope makes an angle of 19 degrees. With the horizontal. So the object is going that way, and it's speeding up. So we draw a free body diagram of the object. And include the fact that the object does have some acceleration right off the bat by means of an arrow that's not touching it. Then let's get the force exerted on the object by the rope. The rope is touching it. Exerts a force that I'll call T for tension. Got an angle in there. I'll define that as theta, 19.0 degrees. And then we got a weight force exerted on the object by the Earth. There's a normal force acting in the upward direction, and a frictional force acting in the direction opposite to the direction in which the object is going. I'm going to check, make sure I got them all. Check everything that's touching it. The rope is touching it. Got to cover. There's a tension force. It's actually an asphalt driveway. I may have called that the floor, but it's an asphalt driveway touching it. It can exert a normal force and a frictional force. Got both of those on there. And then I get the one force that's exerted on the object by an object that's not touching it, namely by the Earth, that weight force. And this is the free body diagram for part D. And that takes care of SAC 113, problem number 1.